Good morning, guys. Welcome to the revision class on digital electronics. As everyone knows, the topics number systems, Boolean algebra, and logic gates, then K-map, then combinational circuits, sequential circuits, A to D and D to A converters, then CMOS logic gates, then semiconductor memories. These are the topics, these are the chapters. In this, from this area, we have been getting 2 to 4 marks. In that, mostly we may be getting question from either number systems or logic gate implementations or K-map. And in this area, we have been getting, right, minimum 2 marks or sometimes 4 marks also. In that, most important area is adders, propagation delays of adders, and different adders which we have, and maximum frequency of operations. Then multiplexer. The most important area from combinational is a multiplexer. Then decoder. These are the areas we have been getting questions from combinational circuits. So one is a adder, different adders, then multiplexer, then decoder. Most frequently we have been getting questions from combinational. Coming to sequential, as everyone knows, most of my students are aware of this, a minimum 4 marks and maximum 6 marks from sequentials. In that, as we addressed earlier, they might be focusing on very basic fundamentals of sequential elements like memory element, cross-coupled NAND, NOR, or maybe reasons for indeterminate state. You need to understand. That is basic elements. Then sometimes we have been getting questions from flip-flop conversions also. Then counter analysis, synchronous as well as asynchronous. Then calculating minimum clock period, maximum clock frequency of synchronous as well as asynchronous. In the recent years, they have been giving questions based on setup, hold, also minimum clock period, maximum frequency, or you may say that setup slack or hold slack, or setup margin or hold margin. So after this FSM, Mealy-Murray machine implementations, and what is the minimum number of flip-flops required to implement an FSM. This type of questions frequently we have been getting from sequential. Minimum 4 marks, maximum 6 marks we have been getting from only sequentials. Then coming to A to D, then basics of conversions, calculating step size or resolution when it is given data, maybe giving analog range, maybe giving logic 1 reference potential, maybe giving full scale voltage. So depending on given parameters, how to calculate resolution. Then when it is given what is the analog equivalent of digital information by giving data with respect to digital to analog converter, and also analog to digital converter, mostly they have been asking questions, what is the conversion time, what can be the maximum sampling frequency allowed, what can be the maximum analog signal frequency can be converted to digital. So based on conversion time, you can decide all these. And also we have a limitation on conversion time with respect to sample and hold circuit. So what are the parameters of sample and hold circuits? How those are going to affect conversion time? That what we have discussed already. Coming to CMOS, CMOS and semiconductor memories, we may be getting 2 marks. From these two, we may be getting 2 marks. Sometimes they may be giving 2 different questions from, right, CMOS as well as memories also. CMOS, as everyone knows that what is the minimum number of transistors required, or how to implement a logic function, or by giving implementation they are asking what is the implementation or what is the logic function it is implemented. This type of questions we have been getting. And also coming to memories, and when specifying a logic function, they may be asking what is the memory size required to store this logic functions, like ROM. What is the ROM size required to store this logic functions? Or by giving a ROM implementation, they are asking that for so and so address, what is the data we are getting? So that we can analyze from discussions we had, right? So when address is given, we come to know that which are the transistors or which are the diodes are going to be on, what can be the outputs, what can be the data we are getting. So when we are giving address, it is highlighting specific memory location and we are getting data. So that we can address, that we can understand from the given ROM circuit, ROM implementation. And coming to RAM, we have SRAM and DRAM. Mostly they are focusing on differences between SRAM and DRAM, and also why it is faster, why it is slower, and what is the number of transistors, what is the density, what is the memory density we had in SRAM and DRAM. So like that, they have been focusing on semiconductor memories. So these are the topics we are going to just revise, right? So first let us see number systems. Coming to number systems, very simple thing is conversion, right? How to convert from one number system to another number system. Then complements, coming to, right, r's complements and r minus 1's complements. Then the most important area where we have been getting frequently questions is signed number representation in binary. When we have both positive and negative numbers, how it is represented? What are the representations we have? Signed magnitude, 1's complement and 2's complement representations. What are the rules for representing the signed numbers in these 3 representations, and which one is preferable and why? So then maybe framing a theory questions on subtraction using complements. There is a possibility for framing a theory question on subtraction process, either 2's complement subtraction or 1's complement subtraction for binary, or it may be r's complement or r minus 1's complement subtraction. So let us see a simple examples how to do conversion. So when we want to convert a decimal number into the required number systems, as everyone knows that we have done different examples also. So a number is given which is in decimal, which is having integer part as well as fraction part. To convert integer part into required base, we go with successive divisions of decimal integer part with required base and accumulating reminders in reverse order. Coming to fraction part, decimal fraction part is multiplied with required base and every multiplication is producing integer. Those integers should be considered in the same order it is produced or original order. So once again what we can say, converting from decimal to any other required base, so decimal integer part should be divided with required base, then it is producing reminders. Every division is producing reminders. These reminders must be considered in reverse order. Coming to fraction part, decimal fraction part is multiplied with required base and accumulating integers produced in original order, in same order which is produced. That is decimal to any other required base. And if I say that any base to decimal, a simple process we can do that. So simply adding weighted values of each and every digit, or what we can say here, summation of weighted values of all digits. Once again, whenever it is required to calculate decimal equivalent of any number which is in other than decimal, then calculate summation of weighted values. So we are calculating weighted values is nothing but digit and its weight, positional weight. So positional weight is multiplied with the digit and it is getting weighted values. Then taking summation of weighted values is giving decimal equivalent. Decimal equivalent. That is the process of converting from any base to decimal. Any base to decimal. Then, and as we discussed, one more process is there, b power n to b. B power n to b. Simple example is octal to binary, hexadecimal to binary, or base 4 to binary, or we can say base 9 to base 3. So wherever it is satisfying that b power n to b, so we observe that every digit can be independently or individually can be converted to the required base b, and using compulsory n digits. Every number or every digit should be converted to the required base independently or individually, must use n digits when you are converting from b power n to b. Whether it is required or not required doesn't matter, but compulsory every digit should be represented with the n digit equivalent in base b. So simply digit by digit we are converting. It is not required to convert entire number into required base. Simple thing is, so digit by digit we are converting into the required base b by using n digits. So that is b power n to b. And another thing is b to b power n. Lower base to higher base when we are converting. Lower base to higher base when we are converting, which is satisfying b to b power n. A simple process is finding sets of n digits and finding decimal equivalent of each set individually and using respective symbol for decimal equivalent. Once again, so while converting from b to b power n, first thing is finding sets of n digits and finding decimal equivalent of each set individually and using respective symbol for decimal equivalent. That's what we do converting from b to b power n. If I say that, simple example, is a given octal number. I want to convert it into hexadecimal. So what we do here, general process we can do that converting to decimal to the hexadecimal also can be done, but if you are applying b power n to b and b to b power n, in 2 steps it can be completed. So it is octal to binary, we can write 6 is 110, 0 is 000, 1 is 001, 3 is 011, 7 is 111. This is the binary equivalent of given octal. Then we need to convert this into hexadecimal. For converting this into hexadecimal, we need to group 4 digits. It is 4, and when number of bits is not sufficient, appending zeros. Again here we do 4 and again appending 2 zeros. Then what we get here, 0001. What is now here we are applying? Binary to hexadecimal, which is nothing but b to b power n. 0001 is 1, 1000 is 8, and 0001 is 1, and 0111 is 7, and 110012, which is C, that is hexadecimal equivalent of given octal number. So what we have applied in this b power n to b and again b to b power n. we applied two processes. One is b power n to b, other one is b to b power n. Octal to binary is b power n to b, and binary to hexadecimal is b to b power n. That's what we are applying here, the process converting from octal to hexadecimal. And one more example, let me consider. If this is a C9 F B7 is a hexadecimal number. Now you want to get a octal equivalent of this. Octal equivalent of this. So given number is in hexadecimal, we want to get octal equivalent. Once again we can apply b power n to b and again b to b power n. So what we can do now, hexadecimal to binary is C1100 and 9 is 1001, F is 1111 and B is 1011 and 7 is 0111. It is a binary equivalent of given hexadecimal. Now you want to get octal equivalent. For that we need to group 3, 3 and 3 and again 3 here. Then 3, 3 and again appending a 0 here. Appending a 0 here. Right. Then what we get here, 110 is 6, 010 is 2, 011 is 3, 111 is 7, 101 is 5, 101 is 5, 110 is 6. That is octal equivalent of given hexadecimal number. Converting hexadecimal to binary, again binary to octal. This is a process. In this we are using b power n to b as well as b to b power n. B power n to b as well as b to b power n. So that is a simple conversions everyone can do. It is a very simple topic. Maybe getting questions sometimes from this conversions. And next thing is by giving an equation, they are asking you to find the base values. By giving an equation, they are asking you to find the base values which can satisfy given equation. Once again, by giving an equation, they are asking you to find base values which can satisfy given equation. Let me take one simple example. So, square root of 121 is equals to 11. Square root of 121 is equals to, it is 11. Then what is the base value which can satisfy this equation? We need to calculate base values which can satisfy this equation. As everyone knows that we have assumed a variable for base, then we are calculating decimal equivalent of each number. Next thing is what? Calculating decimal equivalent of each number. X power 0, x power 1, x power 2 are weights. Again x power 0, x power 1 are weights. Then what we get here? Square root of x square plus 2x plus 1 is equals to, what we get here? X plus 1. To eliminate this square, what we can say here? X square plus 2x plus 1 is equals to x plus 1 whole square. As we are in decimal, I can apply all the decimal operations. 2x plus 1 is equals to x square plus 2x plus 1. Then I am not getting any value for x with this equation. So any value of x can satisfy this equation. So it is any base. It is any base. But base cannot be 2, base cannot be less than 2, because the most digit in the given equation is 2. So base cannot be 2, base cannot be less than 2. Then what we can say here? Any base which is greater than or equal to 3. So it is true, or this equation is true from base 3 and above. So this type of questions already we have discussed. One more example I have considered, a simple process how we are calculating base values. So assuming a variable for base, we are calculating values for assumed variable, then we are validating. So what we are doing here, assuming a variable is x, converting each number into decimal, then we are observing what is the values for assumed variable, which is base, we are getting. So I'm not getting any x values here. So if it gets cancelled, I'm not getting any x value. But if you are observing clearly what is the x values, it can satisfy this equation. So it can be any value. If it is any value, we can say it is any base. If it is any base, then again we need to check what is the most digit in the given equation. In the given equation, the most digit is 2. So base cannot be 2, base cannot be less than 2. Reason behind this is in a number system with radix r, decimal equivalents of symbols must be ranging from 0 to r minus 1, or base must be greater than all the digits used in the number. So 0 to r minus 1 are decimal equivalents of numbers, and base or radix is r. So once again, what is it here? Radix is r. In that, it is possible to have a decimal equivalent 0 to r minus 1 only. That means to get a validity, 2 is a valid digit from base 3 and above. 2 is not a valid digit in binary, it is 2. So in 2 we have only 0 and 1. To make it 2 is a valid digit, it must be from base 3 and above. So it is any base greater than or equals to 3 is the correct answer for this question. Right. So what we have seen, how to convert one number system to another number system, then how to calculate base values for given equations. These things we address. Now let us see complements. Complements. What we know about complements? We have r's complements, we have r minus 1's complements. Second one is r minus 1's complements. So everyone knows a number is in radix r, then we are trying to calculate r's complements and r minus 1's complement. How to get r minus 1's complements? Subtracting all the digits from r minus 1 itself. So whenever it is required to calculate r minus 1's complements of a number which is in r, radix r, then subtracting all the digits from r minus 1 itself. So whenever it is required to get r's complements, then we add 1 to the least significant digit of r minus 1's complements. Once again, so whenever it is required to get r's complements of a number which is in radix r, then add 1 to the least significant digit of r minus 1's complements. So let me take simple examples, and after this we addressed one more important thing about r's complements. So instead of depending on r minus 1's complements, what we mentioned, directly we can get r's complements also. How can we get that? By leaving least significant zeros as it is. First non-zero least significant digit should be subtracted from r, and all the remaining digits should be subtracted from r minus 1. Once again, so r minus 1's complements directly we are getting, but to get r's complements, we are using r minus 1's complements. Instead of using r minus 1's complements, directly also we can get r's complement. How can we get that? By leaving least significant zeros as it is, subtracting first non-zero least significant digit from r, and subtracting remaining digits from r minus 1. So that's what we use methods. Let me take a simple examples. So if I say if this is the decimal number, I would like to calculate 9's complements and 10's complements of decimal number. This is decimal number for which we need to calculate 9's complements and 10's complements. If I say 9's complements for decimal number, which is r minus 1's complement. As we mentioned, r minus 1's complements can be calculated by subtracting all the digits from r minus 1 itself. Once again, so decimal number r equals to 10. We want to get 9's complement is r minus 1's complement. Then subtracting all the digits from r minus 1 itself. What is it here? 9, 3, 9, 808975999. What is this here? 9's complement of given decimal number. What we have done here? Subtracting all the digits from 9 itself, because 9's complement is r minus 1's complement of a decimal number. To get 10's complement, one method we can use by adding 1 to the least significant digit of 9's complement. 9 plus 1, what we get here? 10, 10, here it is 6, here it is 7, 9, 8, 0, 8, 9, 3, 9. What is it here? 10's complement. That is one process. Another process is directly by observing given number and writing 10's complement, which is r's complement. What is it here? Two zeros, least significant zeros as it is. First two non-zero should be subtracted from r, which is 10. 10 minus 4 is 6. Remaining all the digits should be subtracted from r minus 1, which is 9. What we get here? It is 7. Then 9, here it is 8, then 0, then what we get here? 8, here it is 9, 3, 9. So, subtracting all the remaining digits from r minus 1, r minus 1. So, let me take one more octal number. It is octal number. We need to find 7's complements and 8's complements of octal number. So, given number is in octal, we need to find 7's complements and 8's complements of octal number. So, to get 7's complements of octal number is r minus 1's complement. Directly subtracting all the digits from 7 itself. 7, 6, 7, 1, it is 2, it is 5, 7, 0, 2, 7. What is this here? 7's complements of given octal number. How to get 8's complement? Adding 1 to the least significant digit of 7's complement. 7 plus 1, 8. But we are in octal. 8 in octal is 1, 0. It cannot be a symbol 8, because valid symbols in octal is 0 to 7 only. Valid symbols in octal is 0 to 7 only. So, in radix r, 0 to r minus 1, we have symbols for decimal equivalent 0 to r minus 1. When we are coming to r and above, we are using more number of digits than 1 digit. So, what we can say here? 7 plus 1 is 8. 8 is nothing but 1, 0. So, 1 plus 2 is 3, 0, 7, 5, 2, 1, 7, 6, 7. So, instead of using this addition method, I can go with the direct method for getting 8's complement, which is r's complements. How do we get that? Least significant 0 as it is. First non-zero should be subtracted from r, which is 8. 8 minus 5 is 3. Remaining should be subtracted from r minus 1, which is 7. So, what we get here? 7 minus 7 is 0. 7 minus 0 is 7. 7 minus 2 is 5. 7 minus 5 is 2. 7 minus 6 is 1. 7 minus 0 is 7. 7 minus 1 is 6. 7 minus 0 is 7. So, this is another way of getting r's complement of a given number. R's complement of a given number. Now, coming to next, if I take a binary number 0, 1, 0, 0, 0, 1.10101010. This is a binary number. And we mentioned, or I mentioned, a specific method for getting 2's complement directly. 2's complement directly. What is 1's complement? Complementing all the bits, right? So, if I take that 1's complement, 1, 0, 1, 1, 1, 0, 0, 1, 0, 0, 1, 0, 1, 1. What we have done here? Complementing all the bits, changing from 0 to 1 as well as 1 to 0. 0 to 1, 1 to 0. We are complementing all the bits is resulting 1's complement. If I want to get 2's complement, adding 1 to the LSB, that is one method. Another method is, what is that? Till the first non-zero LSB as it is, remaining bit should be complemented. Remaining bit should be complemented. 1, 0, 0, 1, 0, 0, 1, 1, 1, right? 0, 1, 0, 1. So, once again, what is it here? Leave least significant zeros as it is, as well as first non-zero LSB also as it is, and remaining bit should be complement. That's what we have used in getting 2's complement. Once again, to get 2's complement of a binary number, right? Adding 1 to the LSB of 1's complement, that is one method. Second thing is what we can do, till the first non-zero LSB as it is and remaining bit should be complemented. Once again, what is it here? Start from LSB till the first non-zero LSB as it is, and all the remaining bits are complemented. So that is getting 2's complements and 1's complement of a binary number. So getting r's complements and r minus 1's complements of a number which is in radix r. Once again, if a number is in radix r, how to get r minus 1's complements? How to get r's complements? So directly or indirectly. What is that indirectly? Using r minus 1's complement to get r's complement, or directly writing r's complement also we have seen, right? So this is right, getting complements. Next is right, signed number representation in binary. Most important area where we have been getting questions. Signed number representation in binary. Here we have a one by one. What is it here? Signed magnitude. Second one is 1's complement representation. Third one is 2's complement representation. Signed magnitude, 1's complement and 2's complement representation. We have total 3 representations. We know the rules of each and every representation also. Signed magnitude, 1's complement and 2's complement representations rules, we clearly know that. So let me say that if I say signed magnitude, what is it here? Sign plus magnitude. What do you mean by this? MSB is for sign, remaining bits are used for magnitude. If I take one example, 1010, if it is in signed magnitude, its value is excluding sign, we are calculating magnitude. So MSB is 1, it is minus 010 is 2. Decimal equivalent of this signed magnitude representation is minus 2. If I say that 1101, what is going to be decimal equivalent of this? MSB is 1 minus 101 is 5, so it is minus 5. And next, if I say that 111, then so 1111, 1 is minus and magnitude is how much here? It is 7. So if I say that 0001, then what we have here? MSB is 0 positive and 001 magnitude is 1. So 0100, what do we get here? It is plus 4. 0111 is plus 7. What we have range here? Minus 7 is the most negative number, plus 7 is the most positive number. So minus 7 to plus 7. Minus 7 to plus 7 is the range using 4 bits. Minus 2 power n minus 1 minus 1 to plus 2 power n minus 1 minus 1 is the range using n bits. And coming to right drawback of this here, if I say that 0000, it is saying 0. 1000 also it is 0. So to differentiate these two, we say it is plus 0, it is minus 0. In reality, we don't have plus 0 and minus 0, but in this representation it is saying that we have plus 0 and minus 0. That is a drawback of this representation, signed magnitude representation. The range is this and it is having 2 representations for 0. One is saying that plus 0, other one is saying that minus 0. Plus 0 and minus 0. So the range is also minus of 2 power n minus 1 minus 1 to plus 2 power n minus 1 minus 1. Right, that is the signed magnitude. Coming to 1's complement representation. In this 1's complement representation, as we discussed earlier, MSB is having negative weight. MSB is having negative weight minus of 2 power n minus 1 minus 1, and all the remaining bits are having positive weights. Positive weights. So if I consider 4-bit representation, what we get here? Minus 7 plus 4 plus 2 plus 1 are weights. If I say that 1 0 0 0, it is minus 7. How do we get decimal equivalent of a number? Summation of weighted values. Remember this point. So maybe using any protocols, maybe using any rules. So every representation with every protocol, whenever it is required to calculate decimal equivalent, we can go with the summation of weighted values. Summation of weighted values. So weights are changing, but decimal equivalent is always summation of weighted values. What we get here? 1 into minus 7 plus 0 plus 0 plus 0. Decimal equivalent is minus 7. So 1 0 1 0 minus 5. Why? Minus 7 plus 2. 1 1 0 0 minus 7 plus 4, it is minus 3. 1 1 1 0 minus 7 plus 4 plus 2, it is minus 1. 1 1 1 1, it is going to be 0. It is going to be 0 because minus 7 plus 4 plus 2 plus 1, it is minus 7 plus 7, it is 0. Then 0 0 0 0 also 0. So to differentiate this, what we say, it is minus, it is plus, because MSB is 1. So 0 0 0 1 is plus 1, 0 1 0 0 is plus 4, and 0 1 1 1 is plus 7. So finally what we are saying here, again the range is minus 7 to plus 7 using 4 bits, minus of 2 power n minus 1 minus 1 to plus 2 power n minus 1 minus 1. And again we are getting here minus 0 is 1 1 1, and plus 0 is 0 0 0 0. So that is a 1's complement representation, right? Signed magnitude. Then we have seen 1's complement representation. The protocols is this, the rules. Then coming to 2's complement representation. Let us see 2's complement representation. As everyone knows that the difference from 1's complement representation is weight of MSB. So here it is minus 2 power n minus 1, and all the remaining bits are having weights like this, 2 power n minus 2, so and so, 2 power 1, 2 power 0. So except MSB, all the remaining bits are having positive weights. MSB only having negative weight, that is minus 2 power n minus 1, minus 2 power n minus 1. So and all the remaining bits are having positive weights, 2 power n minus 2, so and so, 2 power 1, 2 power 0. If I take 4 bits, minus 8 plus 4 plus 2 plus 1. So if I say that 1 0 0 0, it is minus 8. 1 0 0 1 is minus 8 plus 1, it is minus 7. 1 1 0 0 minus 8 plus 4, it is minus 4. 1 1 1 0 minus 8 plus 4 plus 2, it is minus 2. 1 1 1 1 is minus 1. If it is 0 0 0 only, we are getting 0. Otherwise, we are not getting any representation for 0. Plus 1, 0 1 0 0, it is plus 4. 0 1 1 1 is plus 7. So once again, if you are observing the range, minus 8 to plus 7 using 4 bits. So if I am using n bits, minus 2 power n minus 1 to plus 2 power n minus 1 minus 1. And coming to 0, it is having only one representation. These are protocols of 2's complement representation. Signed magnitude, 1's complement, as well as 2's complement representations. 2's complement representations. Signed magnitude, 1's complement, and 2's complement representations. Now, let us see why these are called 1's complement and 2's complement also. A quick revision we can do that. If I say that 1's complement representation, right, 1 0 1 0, decimal equivalent is minus 5. Why? Minus 7 plus 2. If I take 1's complement of this, what we are getting here, 0 1 0 1, it is plus 5. If I say that 0, 1, 1, 1, decimal equivalent is plus 7. If I take 1, 0, 0, 0, what is that here? 1's complement of this. Then what we are getting, it is minus 7. So when I am taking complements, it is getting opposite sign with same magnitude. Once again, when you are observing that, when I am taking complements, respective complements, if I say that it is in 1's complement, it is in 1's complement. So if I am taking 1's complements of respective representations, it is giving same magnitude with opposite sign. And here also taking 1's complement also is giving opposite sign. Similarly, if I go with 2's complement also, 2's complement also, what we say here, 1, 0, 0, 1, it is minus 8 plus 1, it is minus 7. If I take 2's complement of this, what we get here? 1, 1, 1, 0. No doubt it is plus 7. How we are writing the 2's complement? LSB itself is non-zero as it is, remaining bits are complementary. What is this here? It is 2's complement. If I say that 0, 1, 1, 0, decimal equivalent is plus 6. If I take 2's complement of this, what we get here? 0, 1, 0, 1. What is it here? Minus 8 plus 2, it is minus 6. Once again, it is resulting same magnitude with opposite sign. So whenever we are taking complements, it is giving opposite sign with the same magnitude. That is the reason these are called 1's complement and 2's complement representation. Even though we are using our own rules, our own protocols, our own weights, still it is named as 1's complement and 2's complement, because whenever we are taking complements, it is resulting opposite sign. Right. Now, if I say that minus 25 decimal, right, in signed magnitude, 1's complement and 2's complement representation using 8 bits. If I ask this 8 bits, then how to represent? Minus 25 decimal using 8 bits. So what we get here? Simply signed magnitude, sign plus magnitude. So let me get magnitude bits. 25, 2 1 ja, 2 2 ja, remainder is 1, 2 6 ja, remainder is 0, 2 3 ja, remainder is 0, 2 1 ja, remainder is 1. Then what we get here? 1 1 0 0 1 is magnitude. 1 1 0 0 1 is magnitude. But how many bits I need to use for magnitude? 7 bits. So how many bits I need here? Only 5 bits. So let me make it magnitude using 7 bits by appending zeros. The value should be same. It is 25. And depending on sign of the number, you are going to decide MSB. MSB should be 1 because number is negative. So what we get here? Minus 25 in signed magnitude. Minus 25 in signed magnitude. And another thing is getting 1's complement and 2's complement representation can be done directly representing using minimum number of bits and extending sign bit, another possibility. And second possibility is by representing a positive number, taking complements to get a negative number. So if I say that 0 0 1 1 0 0 1 and making MSB is 0, it is becoming plus 25 in all 3 representations. It is plus 25 in all 3 representations. Once again, what is it here? Making MSB is 0, then magnitude bits using 7 bits, then it is resulting plus 25 in not only signed magnitude, it is true in 1's complement and 2's complement. This already we observed. So when we are comparing signed magnitude, 1's complement and 2's complement, there are similarities. What are the similarities? MSB 0 number is positive, MSB is 1 number is negative. That is one similarity. Second one is all positive numbers representation is same in signed magnitude, 1's complement and 2's complement representation. Once again, all positive numbers representation is same in signed magnitude, 1's complement and 2's complement representation. So here what we have here? A positive number plus 25 we have represented in signed magnitude, which is true in 1's complement and 2's complement also. If I want to get minus 25 in 1's complement representation, let me take 1's of this. What we get here? 1, 1, 1, 0, 0, 1, 1, 0. What we get here? Minus 25 in 1's complement representation. And if I want to get 2's complement representation, let me take 2's complement of this. What we get here? It is 1 as it is. Remaining bits are complemented. 0, 0, 1, 1, 1. It is a minus 25 in 2's complement representation. So what we do here? 1's complement and 2's complement. By representing a positive number, taking complements. To get 1's complement representation, taking 1's complement of that. To get 2's complement representation, we are taking 2's complement of that. 2's complement of that. So another way is by representing minus 25 in 1's complement and 2's complement representation using minimum number of bits with weights. After that, then extending sign bit. What is that? Let us see. Let me represent that. So number is minus 25 decimal. I want to represent in 1's and 2's complement represent. Already we have done signed magnitude perfectly with the protocols. So now let us use protocols also for representing minus 25 decimal. So how many minimum number of bits required? 6 bits. So when I say that 6th bit MSB is 1, weight is minus of 2 power n minus 1 minus 1, which is MSB weight when I am using 6 bits. What am I getting here? Minus 31. What is required? Minus 25. What must be added? Plus 6. Then what should I do? 0, 0, 1, 1, 0. It is plus 6, plus 4, plus 2 we are adding. Minus 31 plus 6 is giving minus 25. So this is a minus 25 in 1's complement representation using 6 bits, which is minimum number of bits. Now I want to get using 8 bits means 1, 0, 0, 1, 1, 0, then extend this, then we get minus 25 in 1's complement representation using 8 bits. If I am extending this MSB, value is not changing. Sign extension property. Extending MSB is not changing decimal equivalent value. Is not changing decimal equivalent value. Let us do same for 2's complement representation also. 2's complement representation also. Let us apply same rules for 2's complement representation. So minus 25 using 6 bits. Why we are going with 6 bits? Minimum number of bits required is 6 bits. Then, so MSB is 1. MSB is 1. Then weight is what? Minus 2 power 6 minus 1. So it is minus 32. What should be added? Plus 7 to get minus 25. So 0, 0, 1, 1. 1 is giving that plus 4 plus 2 plus 1, it is plus 7. Minus 32 plus 7, it is minus 25. But yes, minus 25 in 2's complement representation using minimum number of bits, which is 6 bits. I want to get using 8 bits means extending again MSB. So sign extension I can apply minus 25 in 2's complement representation using 8 bits. So one process is taking complements, another process is representing using minimum number of bits, then extending with MSB. Coming for 1's and 2's complement representation, coming to 1's and 2's complement representation, there we can use 2 methods. One is complement method, another one is protocols which we mentioned, weights we mentioned, we can apply to get expected complement representations, right? So let me take one more example. Plus 24 decimal using 8 bits in signed magnitude 1's and 2's complement representation. In 1's and 2's complement. So if I say that 24, 2 1s are 2 2s are, remainder is 0, 2 6s are, remainder is 0, 2 3s are, remainder is 0, 2 1s are, remainder is 1. What we are getting here? 1 1 0 0 0. it is a magnitude of 24. So magnitude bits of 24. Now I need to represent this using 8 bits in signed magnitude. So magnitude should be represented using 7 bits. Let us make it 24 using 7 bits. Then appending a 0. Then what am I getting here? Plus 24 in all. Not only signed magnitude, because as we discussed just now, right? So if it is positive number, all 3 representations are becoming same. Signed magnitude, 1's complement and 2's complement representation. All these 3 representations are becoming same. Once again, whenever it is a positive number, don't apply complements, because what we are representing is positive number, what we required is also positive number. There we don't need to apply complements. We don't need to apply complements. Once again, people are getting confused here. Every time we need to take complements. No. Whenever it is required, there only we take complement. When is it required? Whenever it is required to get opposite sign number. So representing a positive number, if you require negative number, there apply complements. But whenever represented is positive number, required is also positive number, then I don't need to take complement. Once again, so whenever it is required to use complements, then observe whether is it required or not. If required, we need to take complement. If not, we don't need to take complement. What do you mean by this? If required is opposite sign number, then we are taking complements. When required is not a opposite sign number, then we don't need to take complement. Represented is positive number plus 24, and required is also plus 24 in 1's and 2's complement representations also. Then I don't need to take any complements. So that's what we need to observe clearly, right? And one more thing about this signed numbers. Signed numbers in signed magnitude, 1's complement and 2's complement. Sign extension is possible in 1's and 2's complement representation, but sign extension is not possible in signed magnitude representation. Sign extension is possible in 1's and 2's complement representation. Sign extension is not possible in signed magnitude representation. A simple example can give you clarity. If I take a signed magnitude representation, 11001, decimal equivalent is minus 9 in signed magnitude. 11001, so excluding sign bit 1001 is 9 and MSB is 1, it is minus 9 in signed magnitude. If I extend sign bit 111001, its value is not minus 9, its value is now, what is it here? It is 9, it is 16, it is 25, so it is minus 25. When you are extending MSB or sign bit, value is changing. If value is not changing, there we can say that sign extension is applicable. Sign extension is applicable, right? Okay. Now, sign extension is not applicable in signed magnitude representation. Now, that is representations.